Hash tables illustrate that there's a trade-off between memory and time. They can be used to implement both unsorted sets and unsorted maps. We begin with an explanation of the fundamental concept that underlies a hash table. It is that if a key is an integer value, it can be used as an array index. Using a key as an array index has an important advantage. It is that inserting and removing from a table can be done in constant time, because elements of an array can be accessed by their subscript in constant time. But there is also a disadvantage. In exchange for the ability to access elements in constant time, we may need to use a lot more memory. Let's consider an extreme case. Suppose we wanted to store information about a class of 30 students in an array, and the key that we use is their social security number, which is 9 digits. That would mean we would need an array of 1,000,000,000 elements to store 30 of them. Although memory is relatively cheap today, using a 1,000,000,000 element array to store 30 elements would be an extreme waste of memory. Hashing is a way to find a middle ground between the efficient use of memory and time. It is a compromise between the two. As an example, suppose we use the last 2 or 3 digits of the Social Security number. In that case, the table would only require 100 or 1,000 elements respectively. We will see that although that approach reduces the table size, it also introduces other issues. One final characteristic of a hash table is that, unlike a binary search tree, a hash table is not a sorted structure. We will discover why that is true shortly. The idea of using only the last 2 or 3 digits is a simplistic hash function. The primary goal of a hash function is to reduce the necessary array size. As a result, hash functions cannot be one-to-one functions because the codomain is smaller than the domain. Because they are not one-to-one, it must be the case that several values in the domain map to the same value in the codomain. In the terminology of hash tables, we say that a collision occurs when 2 keys map to the same value. In our previous example, in our class of 30 students, it is possible that 2 students would have social security numbers that ended in the same last 2 digits. Because of this nature of hash functions, collisions are inevitable. So one additional design consideration will be how to deal with such collisions. There are some other important considerations regarding what constitutes a good hash function. It needs to be easy and fast to compute. In big O terms, we want to be sure it executes in constant time. Otherwise, the time required to compute it would become the dominant factor in the time required to access elements. It also needs to provide a uniform distribution that minimizes collisions. The opposite extreme would be one where most values mapped to just a few values, in which case there would be numerous collisions. It should involve all digits of a number or all characters of a string. When Social Security numbers were first issued, the first digits had a geographic significance. In our simplistic hash function with the Social Security number, if we were dealing with older individuals who received their numbers in the same state, and we had chosen the first 3 digits, we might get an extremely high number of collisions because of that reason. Folding or compressing hash codes is a technique for further reducing the table size. Depending upon the hash function we choose, the resulting hash code may still be larger than what we would ideally prefer for our hash table. In that case, folding or compressing them further may be necessary. As an example of a folding technique is one that would fold a 64-bit code into 32 bits. In this technique, the high-order 32 bits are shifted 32 bits to the right, and then exclusive ORed with the lower 32. In that way, all 64 bits have some contribution to the final result. There are several techniques that can be used to compress hash codes. The first is to reduce the hash value modulo a prime number. Using a prime number has been shown to reduce the number of collisions. Another technique is reducing the hash value modulo a value n, which is a power of 2. It has the benefit of being able to be computed very quickly by bitwise ANDing it with n minus 1. Let's consider how we might construct hash codes for a variety of different types of keys. If the key is a Java object, we can use the hash code that is provided for all objects using the predefined hash code method. It uses the address of the object as the basis for the hash code. It is defined in the Java object class, so it is available for any object. If the key is a primitive, that method is not available. If it is an integer type, the value itself can be used after folding or compressing it with one of the techniques that we just mentioned, or by using a custom hash function. If it is a floating point type, it can be first converted to an integer using a method like float to int bits, which is predefined in Java, to first convert it to an integer and then apply the preceding approach. Finally, let's consider the case when the type of the key is a string. In that case, we have several options. In Java, because strings are objects, we can use the hash code method. Another option, independent of the language, is to use a custom hash function that factors in all the characters together with their positions. The most straightforward approach is to treat the string as an integer in the base, which is the size of the character set. Next, we consider how to deal with collisions. The first approach is to use a technique referred to as open addressing, also sometimes referred to as closed hashing. There are several approaches. Linear probing is the simplest technique. When a collision occurs, the next location is checked to see whether it is used. If not, that location is used. If it is also used, then the next location is checked, and so on. The problem with this technique is that primary clustering begins to occur because after a number of collisions, the chain of collisions gets longer and longer, resulting in a linear search from the collision point. Quadratic probing is a slightly more sophisticated technique aimed at reducing primary clustering. After checking the next location, it checks the one 4 positions away, then 9 positions away, and so on. Although it minimizes the primary clustering, a secondary clustering can occur. Yet another technique is referred to as double hashing. With double hashing, a second hash function is used to determine the increment of the steps in the search sequence. Beyond these original approaches, a variety of other variations have been studied. An alternate approach to open addressing is a technique called separate chaining. It uses buckets of some kind. Using fixed size buckets is one approach, but its main drawback is that those buckets can become full. A better approach is to use a data structure that is dynamic. An array list is one possibility. Its main drawback is that if it is made too big, it can waste space. and if it is made too small, can require resizing. Using a linked list avoids both of those issues, although it does require links that the array list does not. In either case, if too many collisions are allowed, the size of these buckets can become too large. If they become very large, a linear search is then needed to locate the element in the list. The load factor of a hash table is a measure of how full the hash table is permitted to get before its capacity is increased. Keeping the load factor low enough prevents buckets from becoming too large, and the time required for searching the buckets from becoming significant. When a table becomes too full, increasing the table size and rehashing all the elements becomes necessary. The load factor is computed as the ratio of the number of used elements to the capacity. For example, a 50% load factor would specify that once the table reached half full, its size would need to be increased. The method used for handling collisions influences the ideal load factor threshold for the table. If open addressing is used, a lower load factor is needed, perhaps around 0.5 or 50%. With separate chaining, the load factor can be as high as 0.9. Whatever the load factor, when it is exceeded, the rehashing process occurs. Doubling the table size prevents the need to rehash too frequently. Rehashing requires computing a new hash code for every element in the table, and then inserting it at the new position. The cost of rehashing is amortized when determining the efficiency of the operations. This is similar to what occurs with an array list. Assuming its occurrence is sufficiently infrequent, the added cost will be negligible. Now let's summarize the benefits of the hash table implementation. No key comparisons are required, so keys do not have to be an ordered type. As long as a hash value can be computed, that is all that is required, and hash values can be computed for any type. Both sets and maps can be efficiently implemented using hash tables. And because inserting and removing and finding elements all involve computing a hash code, possibly searching a short list of collisions, and then an array access, all of them are essentially constant. Rehashing is a linear operation because all of the elements of the table need to be rehashed. As we mentioned, this operation should not occur too frequently. Also, its cost is amortized over all operations.